Hi, this is Lee Phillips. I'm the lead engineer for Robot Dreams. We're the company behind the Robby Framework, which this video is going to talk about today. This is the first of a three-part series of videos intended to show what the Robby Framework is, as well as how you can use it to build robotic control programs that communicate with and control all the devices and services to which a robot connects. This first video consists of a slide deck presentation explaining what the framework is and what it does. The second video will be an actual demonstration of how to build a simple robot network using the user interface included with the framework. The network will set up communication with an Arduino using serial communication. The third video will be a walkthrough showing how the network built in the second video can be used within a standard C# WPF program to show the output from the Arduino on a WPF user interface. So, all that said, let's go ahead and dig in. So what is the Robby Framework? Put simply, the Robby Framework is what's sometimes referred to as a robotic middleware product, designed to sit between a central controlling program for the robot and devices or services to which it connects. The goal of the framework is to, as much as possible, take away the tedious work of writing code to connect to devices and services, as well as coordinating the communication between those devices in the central controlling program. This just leaves the code to orchestrate the behaviors and actions of the robot, which is to say, with the framework, you're left with the fun part of the coding. At its core, the framework is a messaging system that passes formatted JSON messages between a central controlling program, referred to as the Master Control Program, or MCP, and its connected devices and/or services. There's four main components to the framework. Those are message schemas, channels, connectors, and networks. Message schemas define the structure and content of all JSON messages that are passed through the system. Within the framework, absolutely any time a message is either updated or accessed, it's validated against the schema. This ensures that for the lifetime of that message through the framework, it will always maintain the proper structure and content. Next, we'll talk briefly about channels. To use a tired old analogy, you can think of channels as highway lanes where messages travel between connected devices and services and the master control program. The thing to understand about channels is that each of them has its own private communication thread with the master control program. This makes it possible for all of the channels to communicate simultaneously with the MCP as needed. Connectors are independent plug-in components that link channels to devices or services or whatever it is that you're going to utilize within your robot. Connectors can be specific to protocols like serial communication or TCP/IP or HTTP, or individual devices like an RP LiDAR device, or even services like Windows 10 speech recognition or Azure Custom Vision, for example. The framework currently includes 8 different connectors, with a number of others in various stages of development. Finally, there's networks. From a usage perspective, you could think of networks simply as a collection of channels. Internally, networks include a component we call the thread master, which is responsible for orchestrating all the communication between channels in the MCP. You could think of it as the traffic cop, sort of, for the highway we talked about earlier with the lanes for each channel. One final thing to understand about networks is that each instance of an MCP will always be associated with a single instance of a network. Okay, so now it's where it gets a little more interesting. Freeform networks of networks. So one of the key design ideas behind the framework is that there's nothing to say that the device that you're connecting to with the channel cannot be another MCP. It can. So if I've got a TCP/IP connector out there set up as a device connector, and that's connected to another PC that's running on another robot, that's just fine. And what we've really done in that case is we've created a seamless peer-to-peer connection with that other PC. There's actually two types of these connections you can make to remote MCPs. To understand how these work, let's go back to this previous slide. Let's have a quick look at this graphic here that has a screenshot from the channel builder dialog. We're going to take a look at this dialog live here shortly. But one thing I want to talk about on it, you can see here where we have connectors on the channel that are connecting either to devices or back to the MCP. You can see you have MCP connectors and you have device connectors. The scenario we've been talking about is if we had a TCP IP connector on the device connector side. What that's saying is that when messages come from that remote MCP, they're going to come in and go straight to the MCP, on the local MCP that is, and it can decide at its discretion what it does or doesn't want to do about that message. That's peer-to-peer. Now, if we drop that same TCP IP connector on the MCP side, then when messages come into it, those messages are going to go directly out to the device connectors on that channel, which means we're bypassing the local MCP completely. This is a remote control scenario. So that remote MCP could be going directly out to the motors on this robot and saying move forward because I understand that's the thing you need to do right now, regardless of what the local MCP thinks. So in this simple pattern, we have the ability for two very powerful different types of communication between MCPs. This kind of networking is really what the framework is all about. That's the end of part 1 of our 3-part series. In part 2, we'll open up the Robby Framework UI and use it to build a simple network. Thanks for watching.